So here we go. We were talking about the current and voltage references. We were looking for some kind of current mirrors, and we looked into Wilson current mirror, and then we said okay, it has a good output resistance, it has a feedback, so it stabilizes faster and better. All that we did last time was the Wilson current mirror. So let us start with the part ahead. Another current source which is very popular, and one of the reason why we said Wilson, there is a how much voltage across that will get, that is the resistance across the source, is very relevant in many applications. So we want to see now, there is another reference available in the book, please take it. This references, both current mirrors and current sources, current voltage references are, I am actually teaching it from Lee, Boyce and Baker's book, okay. So some data if I am missing here, you can go and look at that book. Exact title is not this, but roughly this, Lee, Boyce and is that okay? Okay, so as I said, this is a good chapter there. The values given is essentially for very old technology, 5 microns, but that does not matter, actually the principle behind, we can utilize it to any technology node later, okay. So I will start with the another reference, which is the threshold reference that is called VT reference current source. The advantage of this is it is a good stable source. If I0 increases, we have done already in Wilson, if this current increases, the drop across this increases, so VGS of this increases, so this current increases, this drop increases, sorry, this drop decreases because of the saturation point, this reduces the VGS for this and it feedbacks itself to a constant value as we did earlier, okay. So this advantage of this is that it is a quite stable source, and typically one has to choose this R2 values suitably, and so that a faster recovery is possible. Is that okay? Of course, as I said, this is only to show you what is the way we have done. Wilson has done same thing, but little slightly modified from this is the Wilson mirror which we have said. There is no R2, I think, okay. Here we are given a R2 drop which is VGS for the next transistor, and that changes the current in the other arm, feedbacks to the from here to here and keeps till that adjusts to itself, okay. So thus it has a stability because of negative feedbacks, as we said. Is that okay? This, as I say, please do not write all that, I have written it because I thought maybe I should not miss what I have to say, but other things you can read yourself. Maybe I repeat, the theory is this, any change here is reflected change here reflects back here, and there is a loop going on there, okay. This is the technique behind stabilizing the sources. Is that okay? Okay, this you can write, which is the final version of output currents. The output current is given by threshold voltage plus under root of 2 IN upon beta. What is this value essentially? VGS by R is essentially the current, is that correct? VGS by R is the current, okay. So that is written in the same form, there is nothing very serious, okay. I0 R2 is VGS and VGS is written in this form. So I0 is only a function of VT. VT is normally fixed for a technology, 0.8 volt, 0.7 volt, 0.6 volt, whichever value you fix. However, its temperature dependence is not very good and not very bad either, but let us see how much we have done earlier, and we will not do DCF for this because the modified version of this, which is the source I have shown you, is now shown. Have you written down this expression? We are not going to use this because it has a VT direct function, temperature dependence both from R, from beta dash and from thresholds, okay. So we will like to see, can we improve the TCF for this source, though it is, what is the advantage of this source was? Stable, it's a negative feedback, it's stable. So a modified version of the same which has been created, instead of the resistance we can replace it by some diode, or rather a current, a transistor itself, which is in active mode, that is in saturation mode. Just let us see, anything which you think I have not this, you please look the book, and if there are still varies, I just want to finish this current because next time I want to start with op amps. So I am little fast today, please note down. A better version of VT reference current source is called regulated cascode CS, okay, current source. You can see this part is same, M2, M4, M1, this is same. All that I have replaced is now R by a transistor which is biased by me to my choice, okay, which is this. But what will happen to M4, M3 combination? This is like a cascode, okay, this is like, so what is the advantage of this circuit? Output resistance is boosted up. So one of the major advantage or major requirement of a good current, last time someone was asking what is good current source. The question asked was that whether it is temperature dependent, how small is temperature dependence, how small is the, or how large is the allout, and how much is depending on VDD variations. A good current source should have lower VDD variation, this lower temperature variation and larger R zeros. Those are called good current sources. The current sources given to you in exam, both are bad because they are strongly dependent on temperature as well as VDD, okay. So they were not good current sources. If someone has written good and forgot not, then he is getting 0 on that, okay. दो 0 है ना इसमें good में, तो दोनों में से. So please take it, these are the trivials, but that is how choices are made in real life. Okay, if you have seen this, as I already calculated R0 for a cascode, and if the AC output impedance is around Gm square R0 cube, assuming all transistors same W balance, same lambdas. And if you look at the current now, it is Vt divided by R2, because the maximum voltage across this will be Vt, and this R2 essentially is coming from, oh sorry, the R2 has been, okay, it is essentially trying to say whatever resistance offered here is divided by Vty, this is the one which will give you the current which is equal to I0. Now this analysis which we have done earlier, all that it shows that it is stable because it is a feedback. Now it is only a function of threshold voltage whichever is given to you, so only one temperature dependence, and this is opposite polarity, because please remember one interesting feature you should all remember, resistances normally, if you have learnt earlier, I hope so, some of you have, it has a positive temperature coefficient, that is resistance increases with temperature, but all semiconductor resistors have negative temperature coefficients. Is that correct? Mu is proportional to the power minus 3 by 2. Is that clear? And therefore the semiconductor resistances have minus TCFs, typically 2000, 3000 ppm per degree centigrade, okay. Like N plus transistor source, if you use it, it is around 3000. If you use a poly resistor, poly dope resistor, it can be 2000, okay. So is that point clear? So the resistor in semiconductors are negative temperature coefficient, and that sometimes advantageous, sometimes disadvantage, because both minus may add, the other quantity is plus, it may actually subtract, okay. So in that case semiconductor resistors are preferred over external resistance. You can always put in a board separate resistor, after all this chip is there, you can always put a resistor at the board, okay, but that is never done. Is that correct? That is never done because that will give you positive temperature coefficient. Carbon resistor, carbon shows positive temperature coefficients, okay. So the same source slightly modified gives you better VOV, VOV is VGS minus VT, which is less than this. So typically you can say I0 is threshold by resistance, which you can calculate, and you can see R0 is very high, R0 is, I out is very high. So this is closer to what you are looking for, good current source, okay. Is that okay? read more about it. Now let us start with, this was the part which I should have finished last time, so I just now start with the real one which I am now looking for, there I spend time. The other requirement other than the current source is the voltage reference. What is the word, why it is called reference again? Because this voltage, otherwise you take a power supply directly, that also is a voltage reference, okay. But what is the problem with those power supply voltages? Because they will change with all kinds of things, okay, by the load, by the VDD, whatever the inside transformers, all currents, everything will shift to, though we may stabilize it, though normally most power supplies are stabilized power supply, but there is still a ripple on it, you cannot reduce to 0. So a good reference DC source, because we are requiring now a DC output which is strongly, which is very strong, in the sense that it does not change very much with temperatures, and it also is independent of VDD, okay. Of course the easiest reference how can you create? By using resistors, easiest, the first one, voltage divider, take 2 resistors, take a tap out of it, and that can still do the job which you are looking. So this is a question for those who want to work with analog ladder in future. These days all mixed signal circuits have analog power supply as well as digital power supply, unit is created there. This is management, power management unit, all chips have. They require 1 volt, 1.5 volt, 2 volt, 5 volts kind of supplies they need, and they use what they call as DC to DC converters, okay. Questions to all of you, why DC to DC? I mean if DC is available, just put a divider and take any amount of taps on it, okay. But why do we create DC to DC converters on chip? तो अभी जब पूछेंगे तब आपको बताया, सोचो क्योंकि सब चिप में लगाया जा रहा है तो कोई कारण है, we'll come back to it later. Okay, he has a point, but that has a cost on it, okay, it's not free. Okay, is it visible? Yes. I take care that I remain inside, but you know it's only my thinking I am doing it. The easiest reference, as I say, is can be created by 2 resistance network, or what we call divider, which is R2 upon R1 plus R2. If I take D reference by VDD, then it becomes R2 upon R1 plus R2, and if we take the sensitivity of V reference with VDD, this is VDD by V reference, which is unity, okay. So the sensitivity of reference voltage with VDD is 1, which essentially means every change there is transferred to the V reference, which is obvious. You can see if I change this, output is proportionately changing, so there is nothing I can do about, because you are just using the divider part there. If I do this dV reference by V reference, that is changing by this percentage, so this is same as we say. So if we calculate the temperature coefficient of V reference, I differentiate this with temperatures equations, then I get 1 upon V reference dV reference by dt is equal to R1 by R2 V reference by VDD, and this function. This is TCFR2 minus TCFR1, okay. If you are making the same material resistance, the difference will be smaller, because this 1 upon R term is going to still come, dr by dt may be same, but 1 upon R values are different, so these are not equals. Is that point clear? Otherwise sometimes you may feel why I am putting it, because 1 upon R dr by dt will be same for the same material, but 1 upon R's are different, so these two values may have difference. So one of the criteria is this R2 should be closer to R1, but what does that mean? 50% shifts, nothing more. I cannot do 0.2 VDD or 0.8, I have to do only half a VDD kind of, which is not every time you may require. So it's a good to have simple divider if you are only using VDD by 2, okay, but it is a very strong function of change in VDD. Temperature wise it may not be that strong function if you keep closer, but it still has a problem of VDD, sensitivity is very strong with that, okay. So let us look at it. If this is not very good, what should I do? I replace at least one of the resistor by a transistor, okay. Is that okay everyone? This is trivial. All that I was trying to say that this looked to be simple. The problem it creates is only be close to 50% VDD shifts only are possible, but even then it is proportional to VDD as a variation. Whereas temperature wise you may probably minimize it. Okay, so the next stage we replace the R2 by a MOS transistor in saturation, and we know in saturation transistor has larger resistor, but its value can be modified by VGS itself, okay, because it has a slope, okay, so one can adjust, and W by Ls. Okay, so here is we have made the reference voltages across the diode, of course this is a diode connection. So VGS is V reference, the current in the transistor is through current in the resistor, so VDD minus V reference by R, but we know IDS is beta by 2 VOV square for the transistor, assuming lambda to be very small. So VDD minus V reference is something like this. Solving, we get V reference as VT plus 2 beta R VDD minus V reference, still this V reference is there. So let us assume VDD is very large compared to V reference, then I can leave this V reference here and I can directly write V reference is Vt plus 2 by root beta R VDD by 2. What do you say, this will be a good, you can directly say it is a function of VDD, is that correct? It is a function of temperature, okay. It is also a function of temperature through beta dash, okay. So as far as this dependencies is concerned, does not seem to be a great divider, I mean great voltage reference. For the sake of I have not solved it, as I said I have taken it this from the, this of course I solved, but the next two formulas I just copied. I hope so, I have done some rough calculation, I thought they are done correct, I hope so. Is that okay? Is that everyone wrote? The function V reference is Vt plus 2 root beta R VDD to the power half is the reference. So how do I adjust V reference value? Therefore by adjusting the value of W by L, by adjusting the value of R, and of course the supply which is given to you, okay, that will decide your reference voltage. Please remember VDD is not in your hand. Why? Technology will say 1.2 volt, 1.5 volt, 2.1 volt, whatever they say, that is the voltage you have. So we have no game on VDD, but we can always look for beta which are size, R which is we are actually, can you know what this R could also be instead of this? Another transistor, but which one you will prefer there? A P channel device is much easierly preferred, and then the ratio of W by L will give you this voltage output at this. Is that clear? Just replace a P channel device and gate connected to drain as usual, and then that means the same gate goes to the, so it looks like more like a CMOS, okay, but the input is connected to the output because there are two diodes. Is that clear? That clear? So this essentially gives me this formula, and as I repeat, I had taken it from the book, so I am not saying they are wrong, but the onus of right or wrong with is Mr. Baker, okay, not with me. So it says that SV reference, though I have done it, but in a hurry I did not know exactly whether I roughly got same, but I just copied at the end. I mean nothing very, just differentiate, there is 1 upon this, there is nothing great we are doing, VDD upon V reference, D reference this, and this comes to be Vt times 2 beta R by VDD plus 2, and if you look at the temperature coefficient, this gives me a long expression Vt times TCF Vt minus half but 2 by W by L VDD upon R beta dash T into 1 upon R dr by dt minus 1.5 by T. Is that correct? This 1.5 by T is coming from where? D beta dash by beta dash, that last time we did in the class also I forgot, so I remember while going to main building that I have not given that data to you. Okay, please remember one catch here which I said in the class also, T is here in kelvins, all other things are expressed in part per million per degree centigrade, but when you divide 1.5 by T, T is in Kelvin. So how, if I divide it by 300, how much it will be? Roughly 5000 ppm per degree centigrade. Is that clear? 5000, I think so. Yeah, 1 upon 1.5, yeah, 5000 ppm per degree centigrade. So this, remember that this number looks to be small, but that is giving a huge value for you, okay. So do not think that it is neglected, okay. 1.5 by T is equal to 5000 ppm per degree centigrade, which is a huge number, is that clear? And actually that is the one which offsets most of it, okay. That is the great fun of this part. Okay, so this also reference you can see, though I have not done it, I may next time I will show you a problem, or maybe I will post it on the web, few problems on this. This still has 3000 ppm to 1000 to 3000 or 4000 ppm per degree centigrade TCFs, which is not fantastic. Less than 1000 or 1000 is acceptable, or anything more than 1000 is not very good TCF. If you can get around 1000 or lower, what is the ideal one I want? 0, okay, I want 0. Now I will try to see this word I say 0, can I really get 0? How can I get 0? If two terms, one is plus and one is minus, and I adjust the values of either or one at least, so that the two terms have same value in opposite sign, then TCF can go to 0. And that is exactly what the last part of this today's this will be, what we call band gap reference, okay. And we will show is TCF could be close to 0. If you can make 0 also, but then W by S will be so odd you cannot put it on the chip, and therefore you may probably not be getting exactly 0, but close to 0, okay. So let us see. So this is a voltage reference, no great problems with this, making it is easiest of it, because anyway CMOS there is a sitting there, just connect the gate to the output and you have the divider and adjust W by S to get the ratio you want. So it is the easiest divider they say. In digital circuit this is very often used. Where do you think we use this? This divider is extremely useful in digital circuits. It is also called voltage translator. The reason is, let us say, अभी आजकल के ये कहना statement ठीक नहीं है, but you are using a bi-CMOS chips also with, I mean bi-CMOS means bipolar and CMOS. There are new technologies, rather old one which is recircuiting now, therefore called new. Bi-CMOS started in 1987-88, was given up in 90s, useless. 2005 again, oh let us look at it, okay. So it has come back. So in bi-CMOS this issue may come, that bipolar requires, for example, noise margin or shift point is around 1.2 volt from 0 to 2.4. For a supply of this it may require 0.6, 1.2 supply. So you may have to actually get half of that equal to half of the other, is that clear? CMOS half should be equal to half of the bipolar swing, okay, which may not be same whatever way you do, okay. So you need translators. So there in all digital bi-CMOS circuits a translator is essential, and this the simplest translator they use is a CMOS divider, okay. So please take it why they are using it, because they are not really looking so much temperature sensitivity, because they feel 1 and 0 has enough margin for me, as long as 4 corner design I am in, thank you very much kind of thing. Analog goes haywire, so we are worried there, okay. Is that okay? So please remember these circuits which I show sometimes, you may not feel that they are relevant, but they are relevant somewhere else, and therefore I thought I should show you, okay. Now I will show you another voltage reference. Okay, here is a better reference which is called bootstrap. What is a bootstrap? What is the word bootstrap came from? Some voltage levels are actually pulled up, okay, that is why it is called bootstrap. नहीं ये अभी पहला सर्किट भूल जाओ, अभी सिर्फ इतना ही है, okay. One can say it is not very different from threshold reference which we have done. All that is there, see M3 and M4 are identical, okay, and they are connected in diode form here. So what does that mean? M3 mirrors M4 currents, okay, M3 mirrors, and if these are sizes are same, current in M3 is same as current in M4. Okay. So I have written current I1 and I2, in fact I1 and I2 will be equal provided M3 and M4 are same W by Ls, same thresholds and connected in this fashion, and therefore it will mirror this current into this. Okay. So in real sense I will put I1 equal to I2, but right now I have shown two separate currents. Now this, there is another this is like a feedback circuit which we did just now, is that correct? At VT reference, this is same circuit. So this current goes through R. These are all gates, so no current can go either side. So this all I2 will go through R. Okay. So it will create a voltage drop here. Which is the voltage drop here? Connected hai na? So now you can see the current here is because of VGS1 and this is coming from here. So they will again do a feedback and adjust I1 equal to I2 at the end. Is that point clear? So how much is the current I2? VGS1 by R is equal to I, both I1 and I2. Is that correct? This is what we want to, we did earlier, just that is repeated. Only difference here is this is coming from P channel sources down. Is that okay? The problem starts. Okay, what is the problem? Now if you see, still you forget this, and these are outputs, one is current source, other is current sinks, this is N channel, this is P channel, just connect it here. Okay, I have connected from here, you can also extend this here because they are the same terminals. Now sometimes I showed direct line, sometimes this, so I just thought. Now let us see, is that okay? These currents are these currents and they are transferred to M5 and M6, and right now their W by Ls are same as this is same as this and this is same as this, and therefore same current is flowing in N channel as well as in P channel. Please remember I can make that difference if I need. What do? I increase the size and I have the other currents possible. But normally I may suggest you as an example, if I want 2 I0 current, I never double this transistor. What do? I take another N and put it double. Think of it why this itself is not doubled, but you have another gate and you put another transistor there sinking with 2 W by Ls. Okay. Why preference is given to a separations. Okay. This is thinking. Now let us say, is that okay figure? So I will start looking here. I already said let us say I1 and I2 are mirrored, so equal. I1 flows through VDD to VSS and M5 and M1, I2 flows through M4 to M2, which is what I am saying, this going here, this going here. So VGS1 is I2R, which is same as I1R, same as IR, you can say that IQR. Let us define a current I1 equal to I2 as I quiescent. Why I was started using Q word now? Because this is DC current and going to bias next circuit for your choice, is that correct? So it is called quiescent currents. So I1 is equal to I2 into IQ, and if I write this expression for VGS1, which is VTN 2 I1 upon this, and if I1 I2, this I1 can be replaced by IQ. So I1R drop is VTN plus 2I1 or I2, whichever it is, upon beta n dash W by L1. Okay. So I now have an equation which can be derived simply by VGS equivalence equal to IR drop. Is that clear? VGS of 1 is same as IR of the drop across the resistance. I repeat, those who are not, the drop across this is the voltage here, so there is nothing seriously been done so far. Okay. So I got this expression that IR drop is equal to VTN plus 2I upon beta n W dash L. And once I get this expression, then I am going to write, figure it out. Please remember I is here, I is here. So what does it means? When I calculate such things, it may lead to a, what is called, which kind of equation leads to? Quadratic, or essentially called transcendental. Okay. So what is the problem in transcendental? There is a non-linearity, and since there is a non-linearity, quadratic always we can solve because there is a first order non-linearity. So it is much easier to solve. But if it is second order, third order, you can only do numerically and there is no other technique. very simple Newton-Raphson mini techniques are available to solve such transcendental equation. Okay, is that drawn everyone? So I write therefore I1 I2 is equal to IQ just I substitute I1 equal to I2 equal to IQ. So it is IQR is VTN plus 2 IQ upon beta dash W1 1. I expand this, square it, and this I get this kind of so called first order nonlinear equation or a quadratic term. And if I have a quadratic equation, I can always solve this equation by simple quadratic nature. So the first solution is minus b under root plus minus under root of b square minus 4ac by 2a, same solution. Okay, ये solution आया 1 of Vtn by r 1 upon beta 1 r square plus 1 upon r under root of 2 Vtn beta 1 r plus 1 upon beta 1 square r square. But the other solution also existed for this. What is that solution? IQ equal to 0 also has I1 equal to I2, okay, but that solution we call it as trivial. But this trivial word is good for mathematics, but in real life circuit may actually enter trivial point, and there is no way once those voltages in feedback you have put it, and if both are 0, nothing can be done, circuit will remain switched off even if power supply is on, everything is on. So you may land in this situation at the start sometimes, not necessarily but may start. Is that clear? In case it is there, so how do you start the current source then, or how to create reference then? Okay. So I must actually now come out of that 0 situation. Is that clear? So essentially I1 equal to I2 equation what I wrote, you write down this and I will come back to figure again, so it will be very clear to you. Okay, is that expression drawn? So we come back, basically what was we trying? This VGS1 we were getting equal to IR, is that correct? So if I only draw this line I versus V, and I draw this line, straight line I2, which is V is equal to IR, so a straight line, V is equal to IR is a straight line. And if I see a current through this VGS because of VGS1, it has a square law, okay. So this current is because of the transistor which is giving me VGS1, and when they are equal, what do we mean by equal? These two intersect, when they are equal they two intersect. So this is the point where the VGS1 and this are matching, and therefore Q is the bias point which you are getting, okay, corresponding to this VQ and this IQ. But I just now said I1 equal to I2 can be attained at this point. One is this, one is this. If that happens, then the circuit will never start because it does not have any voltage to change the voltage. Because why it does not change? There is a feedback. If there is no feedback, open loop, it will. It is trying to adjust to whatever value you have got it wants to retain those values. That is the problem with feedback, that is stable. So it makes this point as much stable as this point. So if you are closer here, you will sit here. Is that correct? This feedback word is good for stability. Fair enough. The situation is here, you are now landing in a stable point here, okay. And no way, unless you physically change the value, this can move from here to here, and the circuit which does this is called the startup. Is that correct? Is the word clear? Startup? Startup means if you are per se here, then it should change the voltage so that I1 I2 start flowing. When no current is flowing, obviously this transistor does not get VGS, there is nothing, the voltages are such that everything is 0, so this potential is also 0. Is that clear? No current, open arm, ये 0 पर ही है. Now if this is at 0, when the startup starts, the way startup circuit is, this is R bias, this also can be replaced by what? I can always replace this like this, okay, it is a diode, essentially I am making a diode drop, VDD minus diode drop. Okay. So there is some potential which is larger than, smaller than VDD, but I am adjusting that so that this one diode drop gets me VGS here. This potential is 0 now, is that okay? When everything is 0, this potential is at 0, this potential is at positive value. So what is it creating? A VGS for M7 which is larger than threshold, okay. VGS for 7 should be, VGS for 7 is larger than VT. So what it will start doing, M7 starts conducting. As soon as M7 starts conducting, the I1 starts flowing down, because this current has no path here, no path here, so it starts conducting through M1, is that correct? As soon as M1 starts conducting, what will happen to VGS? It will appear now. VGS by R will appear in I2, other side. Once this sets up some this, now there is a feedback and this voltage will start rising as the VDS starts increasing, is that clear? As this voltage starts increasing, this potential is less 1 VT above, not 1 VT above node 1 voltage, is that correct? That means M7 will switch off, is that correct? Once M7 switches off, now I1 and I2 where feedback paths are taken care, and whenever they will become equal, you will reach stable point of this. So is that correct? Yes. Let us say initially this was at 0, when both currents are 0, this is ground or ground, so this is 0. So there is a VGS sufficiently high because only one diode drop was taken out of it. So VGS was larger than VT for M7, is that correct? So M7 conducts means it pushes the current in M1. Whenever current goes into transistor, what it shows? VGS, otherwise I cannot have current. Inversely saying apply VGS, you get the current, force the current, so it will create VGS. If VGS increases, because I7 is going through, this drop increases, VGS by R current flows, but this current is essentially taken from this arm, current cannot be in hanging, is that correct? So I2 starts flowing. Now I2, whenever I2 this drop and this feedback will keep pushing VDS of this transistor so that these two currents are equal. The way these values are adjusted, that at the point where you reach here, VGS minus VT VGS should be slightly lower than VT, so that M7 switches off, and switches off where? At this point, is that clear? Now we say once M7 switches off, it does not participate. Why? Because once the circuit is on, this remains off, okay. Per se, because of some reasons of fluctuation comes, again it starts changing currents, then it will start pushing the current from here and again bring it to IQ, is that correct? So you achieve a stable bias point by putting a startup, and once startup occurs, it does not participate in the remainder current source behavior, is that correct? So this is the feature of why it is called bootstrap, can you think? I am pulling this voltage up, bootstrap, लेस को खींचते हैं वैसे. Whenever I need I am supplying a VDD, but I need two VDD sir. So what do? I must hold somewhere on an earlier VDD on a capacitor, and the lower transistor should switch off, then it becomes 2 VDD. Okay. So bootstrap can actually pushes the voltages like a doubler kind of thing to more than VDD. And where do you think you need double more than VDD? You need for a short time transients which will do some other time. So this point is stable now, and therefore you have a good stable IQ VQ situation, and one can say now that this circuit only participates till the I1 I2 becomes equal and reaches this value, and once that happens M7 switches off, and therefore the starter circuit does not participate afterwards. Is that clear? So this is only as long as the circuits are, you are not here, otherwise it just switches off. So you are not bothered about it continue to hold there, what do it will not, it will automatically switch it off itself, but per se because of any environmental situation it goes, it will start to pull up again, okay. So it is some kind of a feedback, second feedback kept there to make output reference as much constant as possible. Is that correct? And that is something what this bootstrap circuit is famous for, okay. There is another reference which is very interesting, and I thought it is for similar forms but very interesting. This is called beta multiplier V reference. What is beta multiplier means? So something to do with increase of betas, and there some word is shown here. The kind of circuit I have shown here also requires startup, this is not shown. It is identical similar circuit, so it will also require startup if this node does not become as it should, okay. So right now I am not showing a startup, the startup does exist on the left. Now this is very simple, one p channel mirror and one n channel mirror connected, okay, with a Wilson like resistor sitting here, okay. So why are we so keen about this? We are interested to find this circuit is used, what is called a self biasing circuit, okay, that is used in biasing. I0 is created from this circuit, okay. What is the requirement of a good circuit reference? It should not change with temperature in specific. Of course, it should not change with VDD, but it should not change with temperature very much. Any good word means the variation should be small, whatever variations you are looking. Thermal is the strongest of them, so that people more worried on thermal part, because why thermal part is worrisome? Because chip starts getting heated, okay. So the thermal variations are immediately seen, okay. In analog even it is worse, why? I's are higher than digital, okay. So I square R is even stronger, so more temperature likely to rise in analog parts than in digital. So there is why we say look into constantly temperature varies, okay. All that we did here, if you are drawn the figure, this is my output current, this is my current in this arm, and if they are M3 and M4 are identical, I0 will also flow as in M1 arm. Please remember M3 and M4 are identical in every respect, Vt and W by Ls, okay. Both are p channel device, so they sources current I0. However, M1 and M2 they are not 100% identical, the only difference is that Vt of course is same, but the size of this is some k times size of M1, that is the, why I never say W by L, what should I say really? Because lengths are normally never changed unless you need specifically, otherwise only widths are changed. So widths of M2 is some numbers k greater than 1, okay. No, you can always say 0.8, वो भी कोई गलत नहीं है, but in my assumption k is greater than 1, okay. Now we can see from here this voltage VGS1 is VGS2 plus drop across resistor, the way diodes are connected or way M1 M2 are connected. So I say VGS1 is equal to VGS2 plus this drop, is that correct? So VGS1 is VGS2 plus I0R this, but we know VGS1 I can write as VTN plus 2I0 by beta 1, VGS2 I can write VTN plus 2I0 by k times beta 1, because now size is k times the earlier one. So that I do not have to write beta 2, I write k beta 1 and then I0R, collect the terms of I0 by quadratic equations, and roughly, maybe I should say, to a great extent this may come, but roughly 2 upon r square beta 1 minus 1 upon root k. Is that okay? I0 is 2 upon r square beta 1 into 1 minus 1 upon root k to the power square. Okay, this Vtn cancels, तीसरा line है ना exactly. Okay, so what should I calculate now for this current, this source? The TCF. I like to see temperature dependence of this current source. Okay. अच्छा इसमें V reference कहाँ होगा, आप बता सकते हैं कहाँ से V reference पिकअप करते हैं हम लोग? The VGS1 is essentially referred. This is taken out and that should remain constant with temperature. Is that correct? VGS1 is the reference voltage. Is that clear? VGS1 is the reference voltage. Okay, so let us start. So which resistor I should use, madam? If I want larger R, which material I should use? N plus is the smallest resistor I can create because doping higher means conductivity is higher, resistance is smaller. If I want larger R, then what should I use? Polysilicon. I do not know whether you have reached polysilicon NMOS silicon gate technology in your technology course, but do look at there. The gate is automatically will diffuse same as source and drain. An N channel device it will become N plus, in P channel it will become P plus. Of course you can engineer it, that also can be made N plus if needed. Okay. Okay, so this expression, now I come back and show you on this, let us say I am using polysilicon layer doped to N plus. If I want higher resistor, so what should I do? Two ways I can create higher resistance in poly or any region. क्या कर सकते हैं? Please remember resistance is created. एक मिनट ये सर्किट दिखाने के पहले आपको वो भी दिखाई दें. ये जैसे ऑक्साइड है, यहाँ पर एक यहाँ भी ऑक्साइड होगा और इसके ऊपर पॉली डालते हैं और यहाँ पर फिर एक ऑक्साइड डालते हैं, यहाँ विंडो खोलते हैं, यहाँ विंडो खोलते हैं. This is how resistors are made. So in a this is poly and plus or anything. I can separately dope poly. So what will happen then? What is the extra thing I had to? Another mask, because only for those polys I will have to open and rest I have to close in a lithography. So additional mask, few $1 million. एक resistor डाला इसलिए generally even if it's you want exact resistance of value you can always create. Poly has a sheet resistance of 10 to power 8 ohm per square, which is very huge. Okay, so I can create mega ohms of resistor in fact. Okay, but if I do that I have an issue that I need another mask to create different resistors. Different kinds of resistance in different mask means ऐसा बढ़ता गया, इसलिए generally avoid कर रहे हैं हम लोग. तो इसका क्या होता है? R is equal to RS L by W. RS is high enough, length to width ratio I want to keep small so that the area is small. Okay, so that is how sheet resistance is. RS is decided by the doping in the poly. Okay, so RS known to us for that dope poly, then you can adjust length width to get your exact resistance values. You never play with RS, you only play with length and width. Okay, so this part which polysilicon layer, TCF R is 1 upon this, typically it is minus 2000, this is for N plus poly in the CMOS, okay, that gives minus 2000 ppm per degree centigrade, that is TCF. Okay. For the beta multiplier circuit just shown, for that I0 which I wrote, I can get TCF of I0 is 2 times the TCF of this plus 1.5 by T. Okay. इसको डिफरेंशिएट करो और ये एक्सप्रेशन आता है. अभी तक जैसे कर रहे हैं वैसे ही करो. टेम्परेचर के अक्रॉस डिफरेंशिएट करो हर पार्ट को. Okay. So it gives you 2 into TCF of R or 2 upon R dr by dt plus 1.5 by T. So now this is 2000, so it is minus 4000, this is 1.5, T is around 5000, okay. So oh sorry, this will be plus, I am sorry, 5000 minus 4000, so you have 1000 ppm per degree centigrade as TCF for I0 at 300 degree Kelvin. Now very interesting thing I am going to show you why big time multiplier became very popular also. How much is TCF? Around 1000, that means reasonably within your limit, okay. Not it, preferably I want how much? 0, but at least it is not 0 but not very bad, okay. So V reference is taken from VGS1 which is 2 upon root beta R1 by K plus VTN. I differentiate this with temperature V reference value, okay. So I get T VTN by dt 2 beta R, इसको differentiate किया है ये. That expression anyway I have written to some extent 1 upon V reference times लिखा है but ये यहाँ है. Now one can see from here, if I want this term to be 0, what do you see from here? इसका यदि ये 0 करना है समझो V reference का, तो ये term 0 होना चाहिए. 1 upon V reference dV reference by dt is TCF, is that correct? But if I want TCF to be small or 0, I want V reference differential with temperature should be 0. Now you have two terms. The threshold voltage goes how much? What is the way I said? How many millivolt per degree centigrade? 2.3 millivolt per degree centigrade minus, okay, is the threshold variation with temperature. So you know this, you see the values put here, and you have another term which is R and K, two parameters in your hand. R of course is deciding your VGS1 also, that is reference value. But for these two together, you can fix this value and fix this value to its minimum, preferably 0. Is that correct? If you do that, we say TCF of V reference will be small r 0. So is that point clear why we chose this one? Because we figured it out that these terms I can correspondingly adjust such that V reference can dV reference by dt could be smaller. Is that point clear? This is the feature of beta multiplier circuits in which TCF could be minimized. Even better control of this is what the next circuit, and which is the most popular circuit in the case. What is that reference voltage circuit which is most popular for analog people? Any name? Band gap reference. Why this word band gap has come? सुरभि जी, बैंड गैप वर्ड क्यों आया? कितना है सिलिकॉन का बैंड गैप? 1.2 नॉर्मल, 1.1 से 1.2 तक अलग अलग मेजरमेंट्स हैं. Since the reference voltage you get is typically around 1.2, we call it band gap reference. It is not directly function. To some extent it can be brought from Ni square term as well, e to the power minus Eg by kT. उसमें एक saturation current आएगा भी. So Eg term भी आ रही है, but basically the idea was that the value you get is very close to the band gap of silicon, and therefore we say it is band gap reference. What should be the advantage of band gap reference? It should be as seen from this formulas. It should have lower temperature coefficient, preferably 0. No variation with VDD and 0 variation with temperature. If that happens, you say you have created a good voltage reference. Why do you need good voltage reference? Raj, किसी circuit में good voltage reference कहाँ लगता है? What kind of biasing so far we were showing you? Only by current biasing. But यदि आप एक ट्रांजिस्टर को वोल्टेज से बायस करना चाहें, क्या करेंगे फिर? You need a constant voltage which is generated. Okay. VDD is not good this. So I want a good reference which is constant. Okay. So reference voltage is an essential part of any analog chip. It is separately created and used. Okay. Is that correct? And that is called band gap reference. So let us look at it. What is PTAT? P stands for proportional. Yes. T, 2, 2, proportional to. A stand for absolute, T stand for temperature. Pitat, okay, proportional to absolute temperature, okay. That is, whatever value we reference is directly proportional to T, okay. So it is called pitat. This is going to be the part of my band gap reference. So I thought first let me show you the pitat itself, okay. This itself can be used as a bias, current biasing, okay. You can see here, I can use this itself as a current biasing circuit, okay.
And should be independent of.
Your point of view is well taken. I said this is a part of the circuit which I am going to use in the band gap reference, okay. This does not have good TCF anyway, is that okay? But it is not very bad either as you are thinking. You calculate that proportionality is much better than otherwise, okay. Okay. Now look at it, this is how many, what are these 4 looking for you? 2 p channel current sources and 2 n channel current sinks, 2 p channel, 2 n channel, is that correct? Then this M2 below, M2 is again k times as we did earlier, M2 is k times M1 as far as widths go. There is a resistor R here, अभी तक जो रेफरेंस दिखाया जा रहा है VT रेफरेंस सेम है सर्किट यहाँ तक, बस इस R के नीचे something else we put, 2 diodes we put. Why did I show you this kind of diodes? Because in technology there is always a parasitic transistor sitting, NPN, PNP वहाँ रहेगा ही. If you see a CMOS process, there are always transistors sitting there. The problem there is they should not turn on. So we take care that they never have a beta of more than 1, less than 1 it should be. But there is a transistor sitting there. So if I connect base collector, then I get a diode which is base emitter junction. Second layer, कौन सा अच्छा होगा? Base, I can Lee collector, base emitter direct. I can have base emitter and open collect or short it. There are 3 possibilities which I can do. Base collector junction, collector छोड़ा है और base emitter junction कब लेते हैं और base collector कब लेते हैं बोलो? When I want a higher voltage breakdown systems, I use base collector junction. Lowest doping है ना collector में. When I want a smaller this, I use base emitter junction. So I need a smaller values. So I use base emitter junction as the diode here. Okay. Anyway, as I said, this is your choice, but I am just trying to show you this is how one does. Okay. So there are 2 diodes D1 and D2. Okay. So now you can say again VGS1 is this drop plus this drop. ये जो है ये प्लस ये है, is that clear? Please remember ये जो वोल्टेज है, ये जो VDS है इसका VDS1 इस ये तो सेम टर्मिनल है VGS1 प्लस दिस है. सर ये जरा मिस्टेक हो रहा है इधर. I must tell you this potential is VGS which is same as VDS. This voltage plus this whatever is the drop here must be equal to this voltage plus this drop plus this voltage. But these diodes are taken identical. So to for practical purposes this must be equal to this plus this. Is that clear? So I wrote it, but it obviously was not clear, so I repeat, this potential is this or this equal to this potential plus this, because drop here and drop here is same. Okay. So reference थोड़ा ऊपर है, इतना ही फर्क है, but subtraction में they are equal. Okay. Okay, so what is the diode current? Now here is that band gap word ना, अभी ये थोड़ा obvious यहाँ से हो सकता है. Diode current is I saturation Q to the power VB by NKT, and if I say VB for this is nothing but VDS for the other one, okay, which is same as just now I said. So I calculate VDS1 and VDS2 from this diode currents. Okay. Please remember why I make it K here, because M2 has a size of, VGS2 has a K times beta 1 as the value of beta 2. So now I calculate drop here, I calculate drop here in terms of saturation currents. What is N? Ideality factor. How much is the ideality factor normally I should use for silicon diodes? कितना लेते हैं? 1. Why 1? Because you are in diffusion current limited situation, you are neither in high current side or nor in generation side. So in between e to the power Vb by Kt only, N is 1 there. If you are in a very high injection state, it becomes 1 upon 2 Kt. If you are in a very low current state, which is generation state, and again Qv by 2 Kt. Okay. Otherwise, most cases N is 1 for silicon. Okay. Okay. So if I substitute 2 in 1, then I get nkt ln I sat equal to nkt by q ln I by k I sat plus IR. nkt का थोड़ा मैथमेटिक्स किया, so I get I is equal to nkt by qr ln k. kt by q को many books write Vt, like Boyce writes. For N channel, P channel he puts Vtn and Vtp to separate from this Vt, okay. But many a time I do not do that, so I wrote full name V thermal Kt by Q, okay. So I get now the current in the PTAT circuit, output current is V thermal by R ln K, okay. V thermal is Kt by Q, okay. So I is proportional to temperature, directly proportional to temperature. So this current source is called proportional to absolute temperatures. क्या एडवांटेज होगा इसका? ये करंट सोर्स नहीं, इसका इंपॉर्टेंस क्या होगा इसका एडवांटेज? व्हाट इज दैट इज एडवांटेजेस यूजिंग दिस? वेयर डू थिंक यू कैन यूज दिस? सेंसर, थर्मल सेंसर, आपको टेम्परेचर मॉनिटर करना है ना, एक बार कैरेक्टराइज करिए, जो भी करंट मॉनिटर करेंगे या वोल्टेज ड्रॉप लेंगे, प्रोपोर्शनल उसका टेम्परेचर डिस्प्ले कर सकते हैं. इज दैट क्लियर? सो दिस इज नॉट यूजफुल एज ए करंट सोर्स, बट इट इज यूजफुल एज ए temperature sensor. Is that correct? That's why the word came, proportional to absolute temperatures. Okay, is that clear? Is that so? Don't ask me इसका TCF कितना. Actually इसके लिए TCF नहीं लेना है. We are not using this as a good this. Okay. Okay. So now this circuit is a part of my band gap reference. Is that should be? Is that point clear why I shown you this? Because this is going to be a part of the next circuit, and the advantage here I keep saying is I is proportional to T. Any scale you create, if it is proportional, it's much easier to draw and figure it out. Extrapolation is the easiest thing to happen. So therefore these are used as thermal sensors. Okay. Okay. Now here is the band gap reference, which is most important. This is some Kt by Q source, okay, VTHM. You multiply a gain factor, so it becomes K times VTM. Pass through an adder, so VB plus K VTHM. Add किया इन दोनों को, तो आउटपुट जो है वो VB plus K V thermal है, okay. Is that clear? This is the principle of band gap reference. Now the way it will happen, the two quantities have opposite TCF in polarity. I repeat, this and this have opposite in polarity as their TCF values. This is a function of K, is that correct? So I can always adjust this one value, this may not be adjusted, but this value, so that it exactly becomes equal to the other for its coefficient. Is that clear to you? If that happens, what will happen? TCF of this reference will be 0. So ideal reference can be created. Is that clear? Is the principle clear? Not that this is how I am doing it, the principle is shown here. Whatever VB is added with K times the thermal voltage, both have different polarity of TCF. This values TCF can be changed by K, and since I can change the TCF by K in value by K, I can adjust the value such that the difference of TCF is 0. Okay. That is the trick in making a band gap reference. ये कहाँ से अभी निकाला था, अभी हमने पीटैट निकाला है ना, उसको यूज करेंगे. Is that clear why I showed pTat? Because I am going to use that pTat here now. Okay, for this thermal I will create from there. Okay, is that okay, all of you? Two parts have different polarities of TCF. Values can be adjusted through K, and the difference can be made as close to 0 as is possible. Is it okay, all of you? Okay, now here is that circuit. ये पार्ट कैसा दिख रहा है, बैंड गैप रेफरेंस. ठीक है, इसमें तो कोई चेंज नहीं किया. अब ये आपका नॉर्मल आउटपुट सोर्स है जो आप अभी दिखा रहे थे, ये हटा दो. ऑल दैट आई नाउ डिड इन द आउटपुट सर्किट, I put another resistance which is L times this resistance R. This M2 has a K times the width of M1, but this resistance is L is some number more than 1 of this, and there is another equivalent diode, same diode D1, D2, D3 which is kept here. Is that correct? This is pTat, and I added this much additionally. Okay. So if I do this for a pTat, we just calculated I is equal to V thermal ln K by R. That is the current in pTat. Okay. Just now we derived. Okay. Where is the V reference voltage I am now taking? What is the V reference I am using? Madam, you can right now show pTat only and put this, so you do not have to redraw all of it. Okay, is that okay? That pTat एक block बनाओ और उसके आगे ये लगा दो. Okay. So to pTat circuit I have additional diode D3 and LR resistor series put there, and output is taken across. So what is the output in V reference here? Drop across D3 plus drop across LR is the reference voltage. Please do not draw this again, you got 8 transistors to show, okay, or 2 diodes 10 plus these 2 10. Is it okay, all of you? So V reference is nothing but the diode drop VD3 plus I times LR, the drop across the resistor. VD3 अभी जैसे लास्ट इसमें निकाला वो NKT by I by K sat है. L thermal अभी I current इसका निकाला था into LR, तो ये आ गया. That R cancels, I into R is R cancels. Okay. So I get V reference is L times V thermal into ln K plus V thermal ln I by K sat, K I sat. एक डायोड का टेम्परेचर कैसा चेंज होता है, डायोड वोल्टेज VB का -2 मिलीवोल्ट टू 2.3 मिलीवोल्ट पर डिग्री सेंटीग्रेड चेंज होता है. तो ये है, ये प्लस है, ये तो प्रोपोर्शनल है ना, तो ये प्लस है, ये माइनस है. VD3 का चेंज विथ टेम्परेचर इज माइनस, द राइट टर्म इज ऑल पॉजिटिव, सो इस थर्मल इज प्रोपोर्शनल टू टेम्परेचर. If I adjust L and K, okay, such that whatever is VD3 coefficient for L and K values becomes exactly same with the opposite sign, because this is minus, this is plus. So TCF can be made 0. Is that correct? So what are the choices for us? Choice of L and K. If I use this reference value shown here, for a given normal CMOS technology, I normally use L of 12, K of 8, saturation is current of the order of 10 to the power minus 12 picoamps. Typical I use in microamps, few microamps, 10 microamps, 20 microamps. Okay. I is typically of the order of 10 to 20 microamps, Okay. Saturation current is typically from tens of nanoamps to sorry 0.1 nanoamp to hundreds of nanoamps, or not 100 point tens of picoamps to hundreds of picoamps, okay, or 0.1 nanoamps. K is typically around 4 to 8, L is typically between 12 to 16, okay. And if I try to adjust, please remember, if I adjust these values, the TCF may not become 0, okay, too much, because same values will decide my reference. So please check it that reference voltage, how much accuracy you want, it may be 1.2 or 1.25, anyway you need to have fixed value. So you better try for TCF to be smaller as the first criteria of making this. Because of last 12 to 16 or 4 to 8, this value will not change other than the second or third decimal, okay. So it is not very good, very bad for any way. Typical reference value which you get for these is of the order of 1.2 volt, which is the band gap of silicon. Therefore, this is called band gap reference. What is the TCF value? As small as you think you can, okay, maybe 0 in best case. इसका वैल्यू आया ना, नहीं एक्चुअली आप थोड़ा सा, मैं इसीलिए बोला ना, वो सैचुरेशन करंट आ रहा है ना, एनआई स्क्वायर टर्म से आ रहा है वो एक्चुअली, मैं आपको बोला भी एनआई स्क्वायर टर्म से आ रहा है, ओके। अब यार सर्किट में वही सब फिर पढ़ाने लग जाएंगे ना। थैंक यू वेरी मच।